Hello, as promised, I'm going to record an example problem from Chapter 15. The problem that I chose is 15-91, and let's go ahead and look at that problem to start off with. So 15-91, we have two discs, disc A and disc B. Two discs are sliding. The weight of A is 2 pounds. Let's start with our givens. The weight of A is equal to 2 pounds. The weight of B is equal to 5 pounds. If they are sliding on the smooth horizontal plane with the velocities shown, determine their velocities just after impact. So the velocities shown are the velocities before impact. We have the velocity of A equal to 5 feet per second. The velocity of B equals 10 feet per second. And it has angles given to us as well. We have 45 degrees for A, and we have 30 degrees for B. We're also given the coefficient of restitution. The coefficient of restitution for this collision is going to be 0.6. So with all that information, we're supposed to determine their velocities just after impact. So we're supposed to find the velocity of A, 2, and the velocity of B, 2. That's going to be the velocity of the two of them right after impact. So the very first thing we need to do with any one of these problems is determine if it's a central impact or an oblique impact. Now this one is an oblique impact, and what that means is that the motion of one or more of the objects is not in the same direction as the line of impact. So if you're asking what is the line of impact, the line of impact is a line that connects the center of mass of the two objects. So we have two center of masses there, and we can connect a line between the two. Now in this problem, they've already given us the x-axis right along the line of impact. That's not always going to be the case. It's your responsibility to set up the line of impact and make sure you have that as one of your coordinate directions. The reason is we're going to be dealing with the direction of the line of impact differently from the direction of the from the perpendicular distance to it. So the y and the x-axis are going to have different equations used. So first of all, we're going to handle the x-axis. So we're going to look at the line of impact. In this case, that is the x-axis. And that's typically the axis that's chosen. So along the line of impact, we're going to have two equations that govern the impact. We're going to have the conservation of linear momentum. We're also going to have the equation for the coefficient of restitution. Now I'm going to first write out the equation for linear impulse and momentum. So for linear impulse and momentum, we have the sum of mi vi 1 plus the sum of the impulse forces, sum of the integral of the impulse forces, is going to be equal to the sum of the linear momentums after the impact. Okay, so this is the governing equation, and it's the principle of linear impulse and momentum. Now I wanted to write that first just because I wanted to talk about this linear impulse in the middle here. So this term is a linear impulse, and this term has a force in it. But as we discussed earlier, when you're looking at a system, this is only going to be the external forces on the system. So first we have to choose our system. Well, what is our system in this case? Our system is going to be both discs, discs A and B. So with both discs, they're sliding on a horizontal plane, so the gravity is going to be acting perpendicular to the plane that we're looking at, and that's not going to affect, it's not going to be an external force for the motions that we're looking at, the x and y directions. The internal forces between A and B, those are internal and do not come into play for this impulse. So we really have no impulsive forces going on, so this whole term goes away, and we have the conservation of linear momentum equation, which is the linear momentum before the impact is going to be equal to the linear momentum after the impact. And that's simply the sum of mi vi1 equals the sum of mi vi2. And of course those subscripts I just mean that you can sum up many different objects. In this case we only have two, so we're going to have MAVA1 equals MA or MAVA1 plus MBVB1. So we have MA velocity of A1 plus MB velocity of B2 is going to be equal to MB, might as well stay in the same order, MA velocity of A2 and MB velocity of B2. Now, there's one thing I left out here. And the thing I left out is that we're currently just looking at the line of impact, and that's very important. So this equation is only working along the line of impact, which means we just take the x component of velocity. So VAX and VBX, VAX and VBX. So we're just looking at the x component. We're going to treat the velocity along the y-axis differently using different equations. Okay, I just consolidated the equation there a little bit to give myself some more room. So we have MA VAX1 plus MB VBX1 is equal to MA VAX2 plus MB VBX2. So that's our conservation of linear momentum. There's one other equation we're going to be using along the x-axis, and that's the coefficient of restitution. So the coefficient of restitution is going to be equal to the final velocity of one of them. I'll pick B. And of course, we're still just looking at the x-axis. So VBX2 minus the other, VAX2, over, and now we're going to switch them, VAX1 minus VBX1. The reason we switch them is because after an impact, the relative magnitudes of the two velocities in that direction are going to swap. So in this way, we get a positive coefficient of restitution if we do VBX2 minus VAX2, then VAX1 minus VBX1. So those are the two equations that we're going to use along the line of impact. So let's go ahead and plug in some numbers and solve for some of these. Okay, I'm going to start off with the coefficient of restitution. So the coefficient of restitution was given as 0.6. So we can plug some numbers into this equation. We're going to get 0.6 is equal to the velocity of B in the x direction after the impact minus the velocity of A in the x direction after the impact over VAX1. Well, that's given. We're going to have to take the velocity of A and break it down into its components. So the velocity of A, if we're dealing with A over here on the right-hand side, we're going to say that the velocity of A is 5 feet per second. And we need the x component, which is going to look like that. And we're given 45 degrees, so the x component is just going to be 5 times the cosine of 45 degrees. And of course it's in the negative x direction, so I'm going to call that negative. The y component is going to be negative 5 sine of 45 degrees. Okay, we can do the same thing for B. For B we have 10 feet per second coming down this way. And we have an angle given of 30 degrees. So our x component is going to be a positive 10 times the cosine of 30 degrees. And then we're going to have a negative 10 times the sine of 30 degrees. So we got the x and y components of velocity there. So at this point we're just using the x components. So we're going to take VAX1. VAX1 is negative 5 cosine of 45 degrees. And then we're going to subtract VBX1, which is 10 cosine of 30 degrees. There we go. Now we're going to take the denominator and move it to the other side. So we end up with the equation VBX minus VAX2 is going to be equal to 0.6 times negative 5 cosine 45 degrees minus 10 cosine of 30 degrees. Plug that into our calculator, and that turns out to be negative 7.317. Now I'm going to solve for VBX2, so I get VBX2 is equal to VAX2 minus 7.317 feet per second. Okay, so that's our first equation, and we have it simplified down, so we're going to be able to use that. Now we're going to use the conservation of linear momentum equation. That's this equation up here that we already have written down. We're going to plug in numbers on the left-hand side for the initial velocity. So the mass of A is going to be the weight of A, which is 2 pounds, over 32.2 feet per second squared. And then we're going to have the initial velocity of A in the x direction, which is given as negative 5 cosine 45. Then we're going to add the mass of B, which is 5 pounds, over 32.2 feet per second squared. And we're going to multiply that by the initial velocity of B, which is 10 cosine 30 degrees. Okay, that's the full left-hand side, and that's going to be equal to the mass of A, which is again 2 pounds over 32.2 feet per second squared, times the velocity of A in the x direction after the impact, plus the mass of B, which is 5 pounds over 32.2, times the velocity of B in the x direction after the impact. You notice that all of the terms here have 32.2 on the bottom, so I'm just going to multiply both sides by 32.2 to simplify things a little bit. If I multiply both sides by 32.2, that can cancel out. And we can do a little bit of calculation here. Looks like I'm out of room, so I'm going to erase a few things. Okay, I just made a little bit of room there. So now I'm going to solve the left-hand side of this equation. I have all numbers on the left-hand side, so I can come up with a number of that, plug that into your calculator, and plug that into the calculator, and I got 36.23 feet per second. That's this whole left-hand side here. And that's going to be equal to the right-hand side, which is 2 VAX2 plus 5 VBX2. And now you see we have two equations and two unknowns. Okay, I just made a little bit more room there. So with these two equations and two unknown, I'm just going to take the value for VBX2 that I solved for using the coefficient of restitution equation. I'm going to plug it into the equation that I got for the conservation of linear momentum equation. So I'd end up with 36.23 feet per second. It's going to be equal to 2 times VAX2 plus 5 times, now plug in the equation above, VAX2 minus 7.317. We can multiply this out and move the VAXs to the other side, so we end up with 7 VAX2 equals, multiply the 5 by the negative 7.317, bring it to the other side, and we end up with 72.815. So our VAX2 is going to be equal to 10.402 feet per second. Okay, then we can go up to this equation that we have up here and solve for VBX2. VBX2 is going to be VAX2, which is 10.402 feet per second, minus 7.317 feet per second. So my VBX2 is going to be equal to 3.085 feet per second. All right, well, if you're doing this problem and you just work through all of that, you might think to yourself, okay, I'm done, and just box that. But that's not what we were asked for, right? That's going to be the velocity of A and the velocity of B in the x direction after the impact. but that's only in the x direction. We haven't considered the y direction yet. So to consider the y direction, I'm going to move on to another slide and just put that information we already solved for. So here's a clean slate, and we solved for VAX2. We said that was equal to 10.402 feet per second. And we solved for VBX2, that was equal to 3.085 feet per second. Now we want to consider the y-axis. Now the y-axis isn't always going to be straight up like this. It depends on the problem that you're given. A lot of times you're going to have to set the axes. They won't be given to you like this. So they're not always going to look like rectangular coordinate systems. The x-axis always is going to be the line of impact, which is going to connect the center of mass of the two objects that are hitting each other. So there's our line of impact. The y-axis, or the axis perpendicular to the line of impact, we're going to use different equations for the momentum of each one of the objects. So this is perpendicular to the line of impact. I'm just going to put y-axis in parentheses because it doesn't have to be the y-axis, it just has to be perpendicular to the line of impact. So on the axis perpendicular to the line of impact, momentum for each one of our particles or each one of our objects is conserved. So the momentum of particle A would be the mass of particle A times the velocity of particle A in the y direction before. That's the initial linear momentum of particle A in the y direction. And it's going to be conserved through the impact. So that's going to be equal to the mass of A times the velocity of A in the y direction after the impact. Okay, well you notice in this case the mass of A isn't changing, so the masses cancel out, and we get that the velocity of A after the impact equals the velocity of A before the impact. And that's going to be equal to what we solved for in the previous slide. I'll go back there real quick. You can see in this slide the velocity of A in the y direction was -5 times the sine of 45. Let's go back there and plug that in. So the velocity of A after the impact equals the velocity of A in the y direction before the impact, which equals -5 times the sine of 45 degrees. Very similarly, we're going to have the linear impact of the disk B before the impact is going to be equal to the linear momentum of the disk B after the impact. So that means since the mass of B is not changing, those cancel out, and we get that the velocity of B in the y direction after the impact equals the velocity of A in the velocity of B in the y direction before the impact. If we go back to the previous slide to see what that was, you can see it's right up here, -10 sine of 30. Let's go back and plug that in. And -10 sine of 30 degrees. Okay, so we can go ahead and write out our velocity in vector form. So we have the velocity of A as a vector is going to be equal to 10.402 and then we have the j direction is going to be -5 times the sine of 45 degrees in the j direction. Our velocity of B is going to be 3.085 I minus 10 times the sine of 30 degrees in the j direction. Okay, now we want the magnitude. We can say the velocity of A magnitude is going to be the square root of the squares, which is going to be 10.402 squared plus -5 sine 45 degrees squared, and the magnitude of velocity of B is going to be the square root of 3.085 squared plus -10 times the sine of 30 squared. calculate that out real quick. We'll get the velocity of A equal to 11.0 feet per second squared, and the velocity of B equals 5.88 feet per second squared. That's the magnitudes. Of course, you can also find the angle and the direction of these by doing by plotting them. So we can say the velocity of A, we know it's going to be in the positive I direction and the negative Y direction. So we're going to have our coordinate axes as we set up previously. We have X, we have Y. The velocity of A is going to be something like that, where the magnitude is 11.0, and we have two components to it. The two components of it are going to be 10.402 in the positive I direction, and in the negative J direction going to be 5 sine of 45. You could do the same thing for B. If you need to find the angle, you take the inverse tangent, sine or cosine, and find the angle there. In certain cases, you're going to have to set up one coordinate system in order to do the impact analysis, and then you're going to have to translate to another coordinate system so that you can solve another part of the problem. So it's important to be able to write out this vector in Cartesian vector notation using the coordinate system that you set up, and then translate it to another coordinate system if necessary. All right, well, that's all we have for our example problem. This was example 1591 out of the textbook. Let me know if you have any questions.